All right, so this is a great analogy to talk about the electric field. Imagine a tree in the middle of a field. Having this tree, we mark out distances of 1 meter, okay? From that, hypothetically, let's say that at a distance of 1 meter, in that area, there are 36 leaves that have fallen because it's fall time and the leaves have fallen. We counted 36 leaves right there. But when you measure out 2 meters radius, you measure and you only find that there are 12 leaves. How did I get that? Do you see the pattern? And at 3, I have, what is this idea I'm trying to allude at? The 1 over r squared dependence. So, 1 over r squared. 1 over 1, that's the percentage was 100% of the leaves, so it's 36 leaves, let's say. Next one, 1 over 2 squared is 4, 1/4. So a fourth of the leaves are found in that next area. So a fourth of 36 is 12. And then let's go further. 1 over 3 squared is 1/9. So 1/9 of 36 leaves is 4. So at a distance of 4, you only find, 4 leaves. 4. At a distance of 2, you find 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'm not going to draw the 36 one. You see, as you're closer to the source of the tree, you have more leaves you find in that first 1 meter. At 2, you find a fourth, and at 3 meters, you find a 9th. That's known as 1 over r squared dependence. And now, just simply replace leaves with lines. So this is a concrete example, but if you replace this with lines, and it's not a tree, it's a source of charge. So imagine this, you have a point, that point is a charge, and it has, let's say it's a positive charge, it has electric field lines coming out, right, in all directions. And if you were 1 meter away from that source of charge, you'd find, let's say, 36 field lines. If you're at 2 meters away, you'd find 12 field lines. And this number allows us to see the magnitude of that electric field. Make sense? And let's shift gears over here. So let's copy this problem down for the first whiteboard problem. Okay, so this is the structure. This is what we know. It's the electric field equation, kq over r squared. This is the given, the picture. Look how closely this resembles the force equation. It's missing one of the q's, right? Because electric field is the electric force per charge. And per means divide by, right? So force per charge, divide out a q. That's why the equation looks so similar, just missing one of the q's. In fact, if you add in the q back, so force, electric force, is going to equal QE. Right? Not too surprising. I'm just using a capital Q to denote that. So why are we using a capital Q? Because we're going to think of that as the source of where it is. And we're not talking about the force anymore. We're talking the force per charge at a point P. So at that point P, there is no charge there. But if we were to put a charge there, that's what the force per charge would be. Electric field. That's, we'll find electric field at point P. And then we're going to find electric field at point P prime. We're going to show you that the electric field at those 2 points are different, actually. All right, so how do we tackle this? We first look at the geometry. Right? The geometry of this, we can conveniently slice this trapezoid into triangles that we're familiar with. So let's go ahead and do that. Let's do that in our notebooks. Draw a dotted line like this. This is the most obvious way that I see how to slice this up. Now we have 2 45, 45, 90 triangles, and we also have a rectangle in the center. Okay, well, I'm given that this bottom base is 2D. Well, these are parallel, right? So that means this is D, right? from here to here, that's d. So what's remaining? Just d left, but it's divided equally amongst two sides. It's symmetrical, so it's d over 2. So this distance is d over 2. That's d over 2 from the point to this dotted line. Okay? From the point to this dotted line. Okay, now that we have this, we now know the side of this isosceles triangle. We know Pythagorean theorem. What is this going to be? This is going to be d over 2 squared plus d over 2 squared, the square root of that. That's your r. Agree? Right? I have a 45, 45, 90, so that means the height right there, that's d over 2. I'm sure you guys can see that. That's my r. That's the distance point P is away from this charge Q. The distance point P away from this charge Q is d. Okay? All right, so let's put it together now. We have two sources that contribute to the total electric field. Let's write the electric field together. So it's going to be K, Q. Let's do the easy one. Let's do this one, right? KQ at a distance d. So at a distance d, and we have to square that because we're following the equation. And what direction would that be? If the test charge is positive, it's going to be pushing it. Like charges repel, so it's going to want to go in the positive I hat direction. So I'm going to add in that unit vector I hat right there. I'm going to put in parentheses. Okay? Next part. This charge now. This charge is a little more complicated, right? It's going to be plus KQ again, right? And over R squared. So it's going to be d over 2 squared plus d over 2 squared. Now, what is the direction? Well, the direction is pointing like this, right? That's the direction. It's going to, but breaking into its components, it's going to be negative I hat plus j hat, right? So now let's look at that triangle, though. Negative I hat plus j hat. As a resultant, we have this. That's the direction. But when we multiply by a unit vector means multiply by 1. If we just do that, it's not going to be multiplied by 1. What is this length here? If this is 1, 1, what's that? Root 2, right. So we're multiplying by root 2, so we have to get rid of that extra factor. We have to scale it back. So it's going to be minus I hat plus j hat divided by root 2. And from there, we're done. That's the electric field at point P. Right? It's pretty easy, right? Let's put that. Electric field at point P. Now, from here, we're going to now do the algebra to simplify this equation, to make it a nice, compact, simplified form. And I know you guys can all do algebra. Let's combine like terms. Let's do the fraction. Let's do that right now. And then we're going to come back and we're going to look at the result. Okay? So let's take 5 minutes to try to do this algebra. Geometry. So let's do P prime. You guys see how the steps I did? Let's do the same thing, but P prime. Alright? So you do it with me. I'm going to erase this now. We're going to do P prime now. We just did P prime. Okay. Alright, so the setup's the same. Now that this is my point of interest, let's look at the easy one first. So E equals KQ, and what's the distance? 2D, right? 2D. And don't forget, that's the entire quantity squared. I made a mistake the first time I tried to do this. I forgot to square the 2. Don't make that mistake. It's the whole entire quantity. That distance is 2D. That distance is squared. And the direction, again, it's going to want to push it away, right? and it's going to be in the minus I hat direction. That's due to the charge on the bottom right corner there. Okay, now the same way, we're going to add to this the contribution to the electric field from this top left charge. And it's going to be KQ again, right? KQ again. But what's the distance? Well, it's the same thing, right? The same distance. D over 2, the quantity squared. D over 2, the quantity squared. But now, the vector is a different one. It's pointing down and to the left. So, it's minus I minus j over root 2. Essentially, that is done, right? Now, let's simplify this. Let's simplify. I'm going to do the simplification the same way. Let's try and do the simplification together, see if we get the same answer. I did the algebra. That's how long it took me to do it. I was trying to make sure I got it right. Did you guys work through the algebra? How to simplify this to this? And the simplification steps are on the right-hand side of the board. Just algebra. We'll do the same trick of the combining the fractions. Let me just go through it real quick. I rewrote it, right? The bottom here, you add them together. It's d squared over 2 because you get 2d squared over 4. That simplifies to d squared over 2. But that 2 is in the denominator, so that goes to the top there. Here, I multiplied by root 2 over root 2. And then these 2 become 2. That 2 in the denominator cancels out with that 2. You're left with the root 2 on top. I'm left with the root 2 on top, and now bringing everything down, I have that denominator is 4d squared. So I need to multiply this piece by 4 over 4. And multiplying by 4 over 4, distribute that, and then combine like terms. Combine i's together. Here it is, 1 plus 4 root 2, I. And then the other one is going to be just 4 root 2, and I think this actually is 4 plus. After getting the signs right. There we go. Yes. And so I just recopied it right there. So just 1, I guess 2, 3 or 4 algebra steps. You guys go with that? So the things we need to know is how to simplify fractions, how to simplify expressions that are in fractional form. Then we get to that. But on the test, I think this should be right. You know, at least you get partial credit because this is correct. It's just that this is nice and simplified. And sometimes maybe it's a multiple choice question, and then you don't see your answer because they simplified it. And then it's like, oh no, I gotta do the work to simplify it. Makes sense? So, with that said, that's the example problem. Take a look at the first worksheet problem. It has the same thing going on. Take a look at it. And again, still work on the conceptual problems, but also now work on number 1. Well, I set up the second question now. Okay, so this is the second problem here. This is our situation. Again, we're going to use this equation as our structure. So, who knows this? What's going to be that? Let's fill in the blanks. Right? If I'm interested in point P, this positive charge is going to contribute to the electric field at point P. The next one over, just a little bit over, is also going to contribute. The next one a little bit over is also going to contribute. Every little infinitesimal step has an infinitesimal amount of charge, which contributes to P. So imagine all these lines all going to P. How do I get a mathematical relationship of that distance? Well, drawing a similar triangle, you see that x here is some arbitrary distance, right? So go ahead and draw a dotted line and label that x to some arbitrary point. So this is the distance x. We're going to integrate because we have so many charges and they're infinitesimal. It's basically continuous in the limit, and we're going to do an integral. Summation. Before we did point charges, we summed, right? But now we have so many, and it's almost continuous, so we're going to integrate, right? So we're going to integrate along the x-axis. Obviously, this is the origin. We're going to integrate from 0 to L. That's our limits of integration. And we're going to look at this similar triangle here. So that x here, how do I get that? That's sine of theta. Sine of theta is x over r. Right? So fill that in. That's x over r. Cosine of theta, that's adjacent of hypotenuse. That's d over r. Right? That's how you break down the geometry. That's always the first step of the physics problem. Okay. And again, we already know from the previous problem, obviously r is square root of d squared plus x squared. Okay? Then let's take a look at the concept here. If this bar has a total charge capital Q, some amount, divided by its total length, that's the charge, the total charge per total length. But if I look at the infinitesimal, that would be what? That would be infinitesimal charge dq. D what? Infinitesimal length is dx. Well, you can say, I'm going to say dx. Yes, I can say dl, but I'm going to say dx because x is the variable that I'm using. And L is a number the limits integration. And it's just labeling. You can call it L if you want. Okay, so now that we have this, that's our piece of information that we'll need. Let's look at this. Let's do it in components again, right? Let's look at the x component. To look at the x component, Ex is going to equal the electric field at point P, whatever that is, times by the sine of theta. See that? It's going to be that times sine of theta. Okay? Now, this is the total. Let's do the infinitesimal pieces, right? So if I do dEx, that's going to be dE sine of theta. Right? Put a little d there, right? That's the total, that's the infinitesimal. Now we're going to integrate both sides. Integrate. I'm not going to write in limits just yet, and I'm not going to write with respect to what variable. We're going to see that how it's going to work out. If I integrate this is going to get back e, the x contribution, but this equals this guy, right? dE sine theta. Okay, so let's plug in pieces now. Now it's all like a puzzle. So dE, let's write the E equation. The E equation is E equals K. I'm going to leave some room there over R squared. Right? I'm just going to leave a little room there. Right? You see what I'm alluding to, right? Well, then dE, right? dE is K dQ. Right? And we have this over R squared. Can we plug it in? We can. We have all the pieces necessary. What's dQ equal to? Multiplied by dx on the other side, you get that dQ equals q dx over L. Cool? So we have this integration variable, dx. We can plug that in. We have to plug in sine of theta, right? So sine of theta is x over r. But r is this, so it's going to be x over this. You see that? This squared. So you kind of put it all together. Let's put it all together. I'm going to multiply this by, let me erase this first. Erase this. So we have dE sine of theta equals k dQ over r squared sine of theta. Do you see the substitution? I want to make the substitution. I want to plug in what sine of theta is. I want to plug in what dQ is. Let's plug that in right now. Let's see what we get. I'm going to try and highlight that with a different color. So, dE sine theta equals k. dQ is q x over z squared plus x squared 3/2 dx. Voila! Do you guys see that? Do you see? Let's take a moment there to digest that. I plugged in for this piece. I plugged in for this piece. I plugged in for R. Take a moment to digest that and see. Raise your hand if you got it. If you got the steps. Got the steps? Okay. Cool? Yes? No? All right. So now this is the thing I want to integrate, and we're integrating with respect to x, right? And we have this ugly thing. What kind of substitution are we making? U substitution. Do a U sub and integrate from 0 to L. And let's pause it right there, and then we'll come back to the answer. Let's do that. Okay, so this third problem The situation is this. We have a proton entering an electric field that's negative, in the negative x direction. Okay? So, I'm going to try and animate this with my hand. This proton is going at a certain velocity. At t equals 0, it enters. At t equals 0, it enters. It's going to keep going, but because the electric field is pointing in this direction, as it's going to go this way, it's going to be attracted to go back left, so it's going to actually slow down and come to a stop at 7 centimeters. Okay? So, goes in, it's still going this direction, but it's slowing down, which means it's accelerating the other way because of this negative electric field. Okay? So at a stop, obviously, V final is 0. The question that I'm asking is, well, what is the acceleration? What is that acceleration to slow it down? What is the initial velocity? And what is the time it takes for it to stop? Okay? So, first thing is, start with this. Well, we know E equals kq over r squared, the force per charge. That means, multiplied by q, that would be the force, the electric force. We also know that force is equal to ma, right? The famous second Newton's law. So, to get A, we can just divide by mass. And the mass is the proton mass. So, we get that QE over M equals A. All right. So, do we know Q? Yes. Do we know E? Yes, it was given. Do we know M? Yes. It's mass. We know that. So, this one's actually super easy. We know those three. You plug those in, you're going to get a number. Let me just write down what it's going to be. It's going to be negative 5.76 times 10 to the 13 in the I direction meters per second squared. Alright, so that's what's, after you plug those numbers in, that's what it's going to be. The essential idea here is we're using this equation right here. We're equating these things, and we're saying that the acceleration is hence this. Now, next question, I, the initial, what would be the initial velocity if that's the acceleration? Well, we invoke our Kinematics equation, so I'll write right here. As you guys probably reminder, V final squared equals what? V initial squared plus 2A x final minus x initial. Well, the delta x, right? That's delta x is 7 centimeters. That was given. So this is 7. So we know that that's 7 centimeters. We know A. We know final velocity, 0. We know that. So this is just a simple algebra question to get VI. Cool? Makes sense? So that gets us part A and part B. Time to stop. What's the last tool that we need to use? What's the last Kinematics equation that we know of? Well, it's going to be V final equals V initial plus AT. Right? Again, we know V final. We just calculated V initial if you did the steps. Right? So we know that. We know that. We know A. And again, just algebra step, solve for T. Cool? So this is just purely using Kinematics equations. In the packet, you have the electric field going up. So you're going to have X and Y. It's going to be a little bit more complicated, but you see, this is the Kinematics equations you would have to use. And just basically algebra, no calculus really involved. Got it? Okay? So with the time you may have left, I think you guys could probably finish this third problem fairly quickly and finish up the conceptual problems. And if you need help with the first two problems, obviously raise your hand.